Hello, one and all. In this one, let's take a look at the answer in this question. The radius of a sphere was measured and found to be 25 centimeters, with a possible error in measurement of at most 0.05 centimeters. What's the maximum error in using this value of the radius to compute the volume? This is in the context, essentially, as you know, of differentials. Keep that in mind. So remember that the volume V of a sphere is given by this basic formula. It's 4/3, and then, let's see here, pi, and then r cubed. Okay, so what we're going to do is differentiate this. That's going to give us the following result next. That dv dr is equal to the following. 4/3. Now you're going to bring the 3 down from the r cubed, so it becomes 3 in that position, and then times pi, and then times r squared, and then you simplify this. Notice that over here you have a 3 in this position, so you're going to cancel those, okay? Like this 3 here will cancel with that 3 in the bottom, essentially. So when you do that, it's going to give you over here, for that reason, essentially 4 pi and then r squared. And then, after that, you need to get dv, which is an approximation to delta v. So in other words, dv would be equal to, you multiply it through by dr on both sides, essentially. That's what's happening. You're going to have the following here, that dv is equal to 4 pi r squared, and then here dr. So it's an approximation to delta v. So I want to be clear that this is more or less an approximation to delta v. Delta v represents the actual exact change in the volume. dv is an approximation using the derivative. Okay? That's why here I have like the squiggly equals above my head, because it's an approximation. Very good. Let's move on. So now we are told the following, right? It says that what's the maximum error in using this value of the radius to compute the volume of the sphere? So let's make use of the information. So we are told that r is equal to 25 centimeters. And further, I believe, what else? We are told that essentially dr, which is the change in the radius, that's equal to 0.05 centimeters. So we're going to plug this information in and get an approximation to the change in the volume, which is also essentially an approximation to like the error. So here, I'm going to proceed as follows. I will say that dv now is equal to essentially 4 pi and then 25 squared, and then times that change in r, which is 0.05. Now remember, if you wanted to use the units here, you could use units here. This would be 25 centimeters, and this would be 0.05 centimeters. So if you multiply the centimeters out, it would definitely give you centimeters cubed. And it should, because dv is kind of like the maximum error in the volume, and the units of volume are centimeters cubed. So when I work this out on my calculator, I get a value approximately. So approximately, this turns out to be about 393 centimeters cubed. So that's my dv. Now this also, again, is approximately delta v, which is the actual change in the volume. Okay? When you go essentially from 25 centimeter radius to a 25.05 centimeter radius, okay, which is basically like this number right there, 0.05. So if you add that to the 25, that would be a new radius of about 25.05 centimeters, you see? So this is dv here. Next thing that is often studied is error, okay? So let's look at the error a little bit here. So I'm going to proceed as follows. People will call this different things, so this is often, they'll call relative error. And we use this phrase because relative means relative to, like, for example, a particular value of r, okay? So relative error. Now here, remember that dv, so dv, which comes from the derivative, this is an approximation to delta v, which is the actual change in the volume. So let's make use of this as follows, okay? I'm going to say that it's like this. So delta V, which is the actual change in the volume, divided by that particular value of the volume, that's just about the same, relatively speaking. So for that reason here, I'm going to put approximately equal to basically dv over v. And now that exactly would be equal to the following. Look back over here. We found that up above my head, dv is equal to 4 pi r squared dr. So over here, I'm going to proceed by doing that. This is the following here. 4 pi r squared and then dr over v, but the v itself is the following. 4/3, okay, and then pi r cubed. So now this expression can clearly be simplified. Remember, it's just a ratio. That's all it is, okay? So when I work this out, I'm going to have the pi's would cancel off. Let's go through the process carefully, okay? Like this pi would cancel off with this pi, right? Like the r squared would cancel off in such a way that a single r would be left on the bottom, essentially. And the bottom fraction, 4/3, that would become 3/4, okay? So when I work this out, it's going to look like the following over here. I'm going to have 3/4, flip the bottom fraction. So I'm doing keep, change, flip, okay? So flip the bottom fraction. Beyond that, I'm going to have that 4 from the top. Then in the bottom, I'm going to have a single r left over, and then I'm going to have a dr left over. So to simplify fully, you see also that like this 4 will cancel off with that 4. And for that reason over here, I'm going to say that I have 3 dr divided by r. Okay, so this represents the ratio dv to v. So an approximated change in the volume divided by the volume. And again, this is an approximation to delta v over v. Keep that in mind. So if I work this out here with these specific numbers, remember our r is 25 and our dr, if you like delta r, the change in the radius is 0.05 centimeters. So for that reason, I'm going to do the following here. 3 times 0.05 divided by 25. So when you work this out on your calculator, you might want to also actually multiply this by 100 because it's a percent change really. So when I work this out, I computed this to be about 0.6%. Now one thing that you should note here, because this seems kind of abstract unless you've done this a few times, if you wanted to represent this with a picture, you actually could. So what I mean by that is at least with a graph of some kind, okay? So you have a stronger feeling for what things are. So you may want to just like draw a coordinate system here. And remember the following basic concept, right? That our volume function is this 4/3 pi r cubed. Okay, so think about this. I'm going to represent this more or less. It kind of looks like this, okay? It's an r cubed kind of function. 4/3 pi are constants and then r cubes. It kind of looks like this, roughly speaking. So now imagine that over here, right, like this right here is 25 centimeters. So here, the horizontal axis is r and the vertical axis is v, okay, which is 4/3 pi r cubed. So then what you can do is pretend that basically you're drawing a tangent line. Okay, so what does that tangent line look like? Just kind of approximated, maybe something like this. Doesn't have to be perfect, okay? So that's kind of like my tangent line. And then our delta r, or change in r, is a very small quantity, 0.05. So that would be very hard to show here, so maybe just kind of exaggerate it just to get the idea across, okay? So imagine that this kind of represents, that leg right there, represents the change in r. And now this right there, again, the picture is not to scale, I'm exaggerating things so they can be visualized properly, okay? So that there would essentially represent dv, okay? That on the bottom there, that would kind of like represent dr, if you like delta r. But notice that when you look at this, clearly there's an error. I hope you see that error. There's an error involved in this, okay? So how can I emphasize that error and where does that error exist? Well, you can see it right here. Okay, let me just like enlarge everything a little bit here so it's easier to see still. You see the error exists right here. Let me emphasize it. This is the error. You see this little bit of a straight line that I've just drawn right there? Okay, I'm going to make it red. I hope you can see it. It's a little red segment in that position. So that's the difference between dv and delta v. They're about the same, but not quite exactly, okay? Keep that in mind. So if I wanted to be more precise, this is what I would do. Okay, let me erase this. I'm going to erase this right here. I need to get at the essence of things. So this whole thing right here, okay, and I'm going to move this over a little better. This whole thing right here, this whole thing, okay, that's the actual delta V. It's a little bit different from dV. Keep that in mind by the length of that segment. And so what we are doing here then is the following. By doing this delta V over V and approximating it as dV over V, it's like saying that over here in the picture, I need to add one more piece of information. Like say this is my, right here, this is the V. Okay, that segment is V. So you see, because dV and delta V are very close in length, that means when you take dV and you divide by V, that means delta V divided by V is well approximated by dV divided by V instead. Okay, I hope you can really see that. And again, the picture is not to scale. It's just greatly exaggerated to really illustrate the concept. So I'm just going to kind of zoom in on the whole thing, make sure you can see all of the work from top to bottom. If this has been helpful, thank you so much for watching. Please leave a like and subscribe if you like this kind of math. I'll see you in another video.